Hi, I'm Jeff Groh and welcome back to Calculus 1. Today we're going to talk about Rolle's theorem and the mean value theorem. I like to say facetiously, the cruel value theorem. The mean value theorem is explained very simply by a graph. Suppose you have a function that is nice and differentiable. The height at A is exactly the same as the height at B. Same height. The function is not only continuous, but it is differentiable, which means it has a well-defined tangent line at each point. If the function is continuous between A and B and differentiable everywhere in between, then there has to be some place where the slope is 0. The precise statement of Rolle's theorem is as follows. If f is continuous on the closed and bounded interval AB, 2, f is differentiable on the open interval AB, and 3, f of A equals f of B, then, so there are 3 hypotheses and 1 conclusion. There exists some point C between A and B such that the slope at C is 0. Now, the proof goes like this. If f is identically constant on AB, then we're done. The derivative is 0 everywhere between A and B. Suppose instead that there exists some point x between A and B where f of x is greater than f of A or f of B, since the endpoints have the same height. By the extreme value theorem, f has an absolute max. The extreme value theorem asserts the existence of an absolute max somewhere on the closed interval AB, but it has to be on the open interval because there is a point in between where the height is greater than at the endpoints. Let C in AB be the x value where f achieves the absolute max. This absolute max must also be a local max. since it occurs on the open interval AB. And so, by the last theorem that we did in the last section, C must be a critical point. And since the function is differentiable, it has to be the sort of critical point where the derivative is equal to 0, not where the derivative is undefined. We can handle the case where f is below the endpoints at some point in between A and B in a similar fashion. As a quick example, let's look at f of x equals x squared plus x minus 6. Note that this quadratic factors as x plus 3, x minus 2. If we set that equal to 0, we get x equals minus 3 and x equals positive 2. So at minus 3 and positive 2, this parabola is crossing the axis. By Rolle's theorem, there has to be some place between negative 3 and 2 where the slope is 0. So let's check out that derivative. The derivative is 2x plus 1. If we set that equal to 0, we end up with x equals minus 1/2. That's the place. At minus 1/2, slope is 0. In our next example, suppose we have x to the fourth minus 2x squared. Find all values c between negative 2 and 2 such that f prime of c equals 0. First note that if you plug in 2, you get 2 to the fourth, which is 16, minus 8, and the answer is 8. At negative 2, you also get 8. So this function has the same height at the endpoints. There has to be some place in between where the derivative is equal to 0. The derivative is 4x cubed minus 4x, which will factor. Setting the derivative equal to 0, we get x equal to 0, 1, and also negative 1. Don't forget that negative 1. We're ready to state the mean, or what I like to call facetiously, the cruel value theorem. It only has two hypotheses. Rolle's theorem had three. First, suppose f is continuous on the closed and bounded interval AB, and 2, f is differentiable on the open interval AB. So we have not assumed equality of the function at the endpoints. They can have different values on each side. What the theorem says is that whatever the slope of the secant line is, there has to be some point in between where the slope of the tangent line is equal to the slope of the secant line. So here's how the proof goes. Here's our function. We're going to have the secant line, and we're looking for a point where the slope of the tangent line equals the slope of the secant line. We have y equals f of x and the secant line. The secant line has the equation y minus f of a equals f of b minus f of a over b minus a times x minus a. That's using the point slope form of a line. So here's what we'll do. We'll set g of x to be what you get when you turn this into a function, f of a plus f of b minus f of a over b minus a times x minus a. Then we'll set h of x to be the original function minus g of x. The function and the tangent line are the same at the endpoints. So when you subtract them, you get 0. Now, the function h is the difference of two continuous functions. It's also the difference of two differentiable functions on the open interval ab. So the function h satisfies the hypotheses of Rolle's theorem. That means there has to be some place between A and B, someplace C. Therefore, there exists some point C between A and B such that h prime of C is 0. Let's think about this last condition. H prime at C is f prime at C minus g prime at C. But g is a straight line. Its slope is a constant, f of b minus f of a over b minus a. So all you have to do is move this term to the other side to obtain the conclusion of the mean value theorem. In our next example, we'll verify the mean value theorem for the function f of x equals 3 minus 1 over x for x lying between 1 and 3. This function does have a point of non-differentiability, but that's at 0 and isn't in our interval. This function will be continuous on the closed interval ab and differentiable on the open interval ab, so it satisfies the hypotheses of the mean value theorem. Let's first calculate the slope of the secant line. F of 3 minus f of 1 over 3 minus 1. F of 3 is 3 minus a third. F of 1 is 3 minus 1, which is 2. That's all divided by 2. 3 minus 2 is 1. 1 minus a third is 2/3. 2/3 cut in half is 1/3. We're looking for a place where the slope is 1/3. The derivative of 3 is 0, The derivative of 1 over x I asked you to memorize as negative 1 over x squared. So the derivative will be positive 1 over x squared. Negative, negative makes a positive. We need to solve the equation 1 over x squared equals 1/3. We can take the reciprocal on both sides, and then the square root. X will be plus or minus the square root of 3. But not both of these lie within the interval 1 to 3. Our solution then is x equals positive square root of 3. Let me give you a more practical example. Suppose 2 patrol cars are parked 5 miles apart on a turnpike equipped with radar. A specific car is zapped by them with their radar, and the speed measured as they pass is, say, 55 miles per hour and 60 miles per hour. The measurements were made 3 minutes 45 seconds apart. Show that the car operator must have been speeding. We'll prove this using the mean value theorem. The mean value theorem says that if s of t is the position function, there has to be some point c where the derivative of the position function, which is the velocity function, is equal to position at t2 minus position at t1 divided by t2 minus t1. The difference in times, we have said, is 3 minutes 45 seconds, or 3.75 minutes. The difference in positions is 5 miles. So we have a speed in miles per minute. Converting to miles per hour, 60 minutes is 1 hour. The units of minutes will cancel. We can see then that the speed of the car, the time rate of change of position, must have been about according to my calculator, 80 miles per hour. The officers are fully justified then when they stop the traveler and issue a ticket. Students in my classroom are often astonished by this problem. They wonder, is it possible that these police officers can possibly know the mean value theorem? And the answer is yes. I know a man who earned his PhD in mathematics and then became a police officer for a number of years. So, yes, there are police officers who know the mean value theorem, and there are judges who understand the implications of the mean value theorem as well. I'd like to prove an important theorem. You already know the following fact. If f is constant on some interval ab, then its derivative is 0 everywhere between for all c that are elements of the interval ab. This is an implication. Constant implies derivative 0. The converse would be, if the derivative is 0 everywhere between a and b, then the function is constant. But we've seen before that a theorem can be true, but its converse might be false. So it does take mathematical proof if the converse is to be shown to be true. Let's write this down as a theorem. If f prime of c is 0 for all c between a and b, then f is constant on the interval ab. And let's prove this. The proof requires the mean value theorem. In our proof, we'll suppose f prime of c is 0 for all c in the interval ab, and we'll try to prove that the function is constant using the mean value theorem. We'll let x1 and x2 be elements of the open interval ab, where we'll assume that x1 is less than x2. Then f satisfies the hypotheses of the mean value theorem on the closed interval x1 to x2. Therefore, there must exist some point, we'll call it, in the interval x1 to x2, f prime of c hat equals f of x2 minus f of x1 over x2 minus x1. But wait a minute, the derivative is everywhere. The derivative is 0 everywhere. If we multiply both sides by this denominator and then move this term to the other side, we get f of x1 equals f of x2. Because x1 and x2 are arbitrary, that means the function value will be the same for any 2 points within the interval, and that's what it means to be constant.